So then we go to the next section, which is the bitwise operators, right? So the first operator we have is the AND operator, and it's denoted by the ampersand. And so this is the AND operator, and it's called the bitwise AND. Now it's just like what we that it's the same intuition that we came across with the AND sorry, with this AND operator in the previous video, right? So it's just the same intuition. Now if you have condition A and condition B, right? And then you are evaluating A and B. If A is false and B is false, then the entire thing becomes false. If A is false and B is true, the entire thing becomes false still, because we need two of the conditions to be true in order for a true outcome to be returned. Over here, A is true but B is false, yet the outcome is false. But then if A is true and B is true, then we have a true outcome as well. So that's how it works. We illustrated it intuitively by using a parent and a party example, kind of something. So where both parents have to agree. So if the mother agrees but the father doesn't, the party would not hold. If the father agrees but the mother doesn't, the party will not hold. The mother has to agree and the father has to agree as well before the party can hold, right? And if both of them disagree over here, of course the party cannot come off. So that is the intuition over there, right? And I hope you get it. So this is what we are going to do over here. We're not going to create any variable here. Let's just print it out onto the screen. So we have, remember, these kind of expressions are always in bracket parentheses. Right, so let's go ahead and illustrate with an example. So what we can have over here is, let's just print it out directly onto the screen without putting them into variables. So we have our parentheses over here, and we have, let's say for example, 56 and let's just say 42, anything, right? So we have this over here, and let's run it, and let's see what this would return, right? So 40 was returned over here. Good. So we want to copy this value. Let's write it here, returns 40. So now let's analyze the binary operation itself to see if this value that it returned is true. Now let's go to the web, and then we convert 56 to a binary number so that we know what number we're working with. So let me refresh this page. So we have 56 over here, and we're converting it to a binary number. So we have 111000. Good. So we copy this and we paste it over here, right? So that's 56. 56 is equal to that. Then we want to convert 42 as well. 42 as well. And we have this number over here. So we copy that as well. And we paste it down here. So that was 42. Right. Now let's see what this would evaluate to. Now we know that 1 evaluates to 1 over here. So this would output 1 over here. So this is output 1. Then 10 would output 0. 11 would output 1. 00 would output 0. 01, 01 outputs 0. Right, so 0. And then 00 outputs over here 0 as well. This is the line we're using here. So 0. Now let's copy this and then convert it to a decimal to see if we can get 40, so that we get the intuition of how this really works. So we'll copy this and then we paste. So the number is 101000, right? So we paste it in the browser. So we change this mode to binary and then this to decimal. We paste it, we convert. We should be getting 40, right? So here is the 40 we have. So that's the intuition behind the working of this AND operator, right? So you can go ahead and try with multiple examples, right? So I want to just use this example to illustrate this. So I'll just cut this one. I'll cut it and then paste it over here to illustrate the bitwise or paste. Right, so what we want to do over here is we want to use the OR operator, and over here for the OR operator it just needs one value to be true for the entire statement to be true. Now this is false and this is false, so the entire thing becomes false. The first one is false over here, but the second one is true. Since it needs just one true value for the operation to be true, everything returns true over here. Now one of this is true as well. As such, everything returns true. Now in the fourth case, A is true, B is true, then the entire thing of course should become true, right? Because it just needs one value to be true. Good. So now we have 56 or 42. So let's see what that is going to evaluate to, right? So we go ahead and clear all this output and then comment out this and that, and we'll go ahead to run this program, and we have 58 as the output, right? So put it here, that means it returns 58, right? Good. Now let's see the intuition behind the working of this particular program. We know that 1 1 will return 1, so we output 1 over here. 1 0 would return 1. Since one of the conditions is true, then everything becomes true. Now both of the conditions here are true, so it will return 1. Both conditions here are false, so this is false false, so it returns 0, right? Then 0 1 would return 1, of course, and then 0 over here. So let's copy this and see if that would output, I think 58, right? So we paste this here and then we convert, right? So we have 58 over here. So that means that we've gotten the intuition behind the working of this particular OR operator. Now I'll use this example as well in the third case. So I'll cut it again and then use it in this case. And this is the XOR operator. XOR, and it's denoted by this hat sign. And this is the bitwise exclusive OR. Now over here it's slightly different, but not entirely different. The intuition is almost the same, right? Over here, if you have two like outcomes, then everything becomes false. So condition A is false, is 0, and B is 0. Now everything becomes 0 because condition B and A were the same. They were alike. Their outcome was 0 0. So everything becomes 0. Now we come to the fourth case where they are both alike again. So the B was 1 and A is 1. So everything becomes 0, right? So if they are alike, everything returns 0. But then if they are unlike, if one is false and one is true, or if one is 0 and one is 1, then the total outcome returns 1. So with this in mind, let's go ahead and use this. So we have the bitwise exclusive, or we call it XOR, something like that. Right, so we'll go ahead and then run this to see what the outcome is going to be before we try to get the intuition by using binary format. So now we have 18 returned over here. So let's write here that it returns 18. Good. So now let's go ahead and then use the binary format to see whether what we have is what we want. Now if they are like, it returns false. So 1 1 will return false. Over here they are, this is 1 0. They are unlike, so it returns true 1. Over here they are like, so it returns 0. They are like, it returns 0. They are unlike, it returns 1. They are like, it returns 0. Right, so we copy this and paste it in the browser. So we convert and we have 18 over there. Right, so that's the intuition behind this particular operator as well. Good, so I'll go ahead and comment out this and that, and then we'll move on to the not binary complement. That's a bit inversion operator. Now this operates on one operand. What we call an operand is either A or B. Over here we had two operands, 56 and 42. They were two operands, but this one just operates on one operand, and you see that in a bit. Now what this does is it changes the ones of a binary number to zeros and vice versa. We're not going to look at the binary intuition behind it. We're not going to run it, do the binary operation, because it's kind of different, right? So we'll not just look at that, but we'll look at the output from the decimal format. So let's just say that we have an integer, or should I not create an integer? Yeah, let me just create an integer variable. So integer a is equal to something like 78, right? So now let's output the not, the unary complement of this particular integer. So we have cout, and it's denoted by this particular sign a. We have that. Good. So what this will do is it will return the unary complement of this particular integer, and this is just one operand over here, as you can see. Right, so we go ahead and run this, and we have negative 79. Right, so let's see the intuition behind it. Returns negative 79. You might be thinking, what exactly is the use of this? Well, if you are going into web development, you might not need these ones because you just need some frameworks and other kind of skills to build web. But for people in software development, for people in software engineering and all of these, you might need these kind of details. If you will not be needing this, you can skip this entire video and all other videos that go into detail. But I just felt I should put these videos out there for people who would want to learn. Yeah. So let's go ahead and then get the intuition behind this operation. Now, as I've written over here, when you are finding the unary complement of an integer, what the computer does is it finds the negative of one less than the number. So this will be the negative of 78 plus 1. So 78 plus 1 is 79, and then you negate the entire results. So that's the intuition behind it. So let's go ahead and change this to a number other than that so that we can be sure of this particular generalization that we have made, right? So we have 566 over here, and right, so if it's 566, then that means that 1 was added and negated, right? So this generalization over here is right. Right, so now we move on to the shift bits left operator, and this is how it is denoted. Over here as well, we will look at the binary operation, what happens at the binary level. Right, so what this does is it picks a number. You know that when you input a decimal number into the computer, that means in base 10, it basically creates memory for it in binary format. So it stores it in binary format, not in the format that you have inputted, right? So we can get to the binary form. So the computer basically performs operations on these numbers in at the binary level, and that's what exactly we're trying to understand and do. And if possible to, and it's even possible to always change and then kind of perform operations on them at the binary level as well. This is an integer I created, and it's called a, and it stores a value of 10. You know this already. And then I use the auto keyword to assign the automatic data type to whatever will be returned over here. Now what this operation does is it finds it shifts the bits of this number. So this is the number a, and it shifts the bits of this number to the left 0 times, and this shifts it to the right 1 time, and this shifts it to the right again 2 times, to the right again 3 times. So I did it repetitively so that you guys can see the sequence of events, so that you can get a relation, yeah, of what is happening. So I would run this and then use a Word document that I prepared for you guys to kind of get a graphical representation. So let's see that in a bit. Right, and what I did here is I just printed it. I just printed B, C, D, and E with an end line statements over here to separate the lines, right? So that was what happened over here. Now let's see what happened. When A was 0, the same number was returned over here. 10 was returned. Now when A was 1, that means shift the bits to the left by 1. Then the number was halved. Sorry, it was doubled. It was doubled. So 10 became 20. That means it was doubled. Then when A was 2, then the number was double. It was double. The previous was doubled again, so it became 40, and then 80 over there. We would come back to this one again so that you guys would kind of get a proper intuition. But before then, let us use a Word document that I prepared, right, to illustrate this. Now, where we are is the shift bits left. So we picked a number which was 10, right? And 10 in the binary format is 1010. This is binary format to base 2, 1010. Now if we are shifting to the left by 1, now take note of the color codes that are used over here. When you shift to the left by 1, then you basically this one moves out of the color sequence to the left, and then the 0 moves into the yellow, and this one moves into the green, and this last 0 moves to the blue, and then there is the red one left with which is not filled, so you just fill it with a 0. We did that in the second case where we are shifting it to the left 2 times. So we picked this number and we're shifting to the left 2 times, and that means we shift this one time, right? So the 1 moved further and this 0 came out here, over here, and then this 1 moved into the yellow rectangle, the yellow code, in place of the 0, because the 0 moved out. We are moving to the left, so the 1 became yellow, over as you have seen over here, and then the 0 over here became 1 over here in the green, and then the blue over here was replaced with another 0 0. Then at the end red was left, and you just substitute a 0 in there, right? So that's the intuition at the binary level of application of this one. So let's go back to the code and rerun this to get a generalization, right? So we run this, build and run. Now the first one, now this is a generalization as you might have seen, because this is the first number and it was doubled, this one too was doubled, and this one too was doubled. So this is the generalization that I came up with over here. When you input a number, right? When you input a number, what happens is this is the number of times you want to move it to the left. So what happened over here was it took the number a, then times 2 to the power m. So 2 to the power 0, over here 2 is to the power 0. So 2 to the power 0 is 1, right? 2 to the power 0 is 1. So basically what it did was it multiplied a by 1, and a is 10, so a times 1 will give us 10, right? Then what happened here was, so I'll copy this and paste it over here. Whoops. So this is then 2 to the power 1. So what happened here was 2 to the power 1 is 2. So a times 2. 10 times 2 is what? 20. And we had 20 over there because we shifted it to the left. We have already looked at what happens at the binary stage. This is a general decimal application that we are looking intuitively at the decimal level. Right, so we move on to the third one, and I want to just paste this over here. Whoops. Okay, so I paste it, and then over here m was then 2, right? And 2 squared is 4. 4 times a, which is 10, for that will be 40, and we have 40 over there. And when you continue, you get 80 at the last aspect, right? So that is what happens. That's how it's being evaluated, right? So I'll go ahead and then comment out all of this. So we move on to the next section, right? Then the next one is the shift bits right, and it's denoted by 2 greater than signs, right? So then what I did over here was I just wrote a piece of code that would be very simple to use, like whole numbers. It's not decimal numbers that you have to kind of look at it carefully, right? So this is an integer a, and it's equal to 100, and you know the use of the auto keyword already, right? It assigns automatically the data type to whatever value that will be returned after the evaluation, right? So I use the shift bit right operator over here. So a shift bit right 0, a shift bit right 1, a shift bit right 2, a shift bit right 3. Then after that I printed them over here with the end line statement to kind of give space, move it to the next line. So let's run this and see what would be output on the screen. And we have, when a was 0 we have 100, when a was 1, sorry, When m was 0, we had 100. A1, when, sorry, m was 1, we had 50. So you can see a general trend here that it's been halved. So 100, half of 100 is 50, half of 50 is 25, half of 25 would be 12.5, but 12 was returned. Now we should note that in using these shift bit operators, whether shift bit to the right or left, and even to the left, you don't have decimal numbers, right? But we can use some numbers which have been pointed to see what that would return. So I hope I didn't forget that. Right, so over here we can see that everyone is being halved, and over here we get 12 returned because an integer was returned, the whole number was returned, but the decimal point was done away with. Even I put float over here to ensure that this value that will be returned should be retained as a float, but yet 12 was returned. So you can see that even it doesn't matter of the data type that you have named it a variable with, it will still return an integer, right? So take note of that. So let's look at the binary level application, the binary level. What at the binary level, what's happening, right? So we have the number 100 over here, and this is the binary format of 100 of base 2. I didn't put any base 2 over here. Let me quickly just add it. So we have base 2, right? So this is the binary level of 100. Right now we are shifting to the right. Take note of that, we're shifting to the right. So that means that this first one would move. These are the color codes over here. So after the first one, let's even start from the last. So the 0 moves off the color grade. This last 0 moves off the color grade. So let me even put it over here, right? Oops. Right, so this 0 moved off the color grade, and then this blue graded 0 moves to the I think it's purple or violet, and then the 1 moved to the blue. So we are shifting all of them to the right. Now when you do that to the last number leaves its place to the brown color code. So this place will remain empty, and this 0 would be off the color grade. Now we are only using the ones on the color grade, so this 0 goes away. And when we do this, 110010 is the binary form of 50, and we can see that 100 has been halved. So that is the application over there. When m is equal to 2, when we move it 2 times to the right, we have this one moving 2 times to the right. So we have 1 here, leaving these 2 spaces to the right over here. So we have pushed it 2 times. So in essence, these 2 last zeros will be done away with, so that it will be left with 11001 in essence. So 11001 in essence. So that is application over there. So note that when you're shifting to the right, when the number gets off the color grade, you don't include it in the final computation, because if these two zeros got off the color grade, so you don't include them. Now this will be the final one, and we can see that that's the binary format of 25, and that's the half of 50, right? So that's the application over there as well. And so when we return to this, let's run this again so we can get a generalization formula kind of for this particular computation. So we have 100, 50, 25, 12. So what I did over here was, this is a generalization, and it's n times 0.5 to the power m, where m is the number of times you're shifting it to the right. Good. So we'll go ahead and see what really happened. So now 0.5 to the power 0 is 1. So basically to be a times 1, which is 100 times 1. So this will return 100 as we got over here. Right. Now we move on to, so I'll just copy this and paste it over here. Now we move on to m equal 1. Right. When it's equal to 1, we have 0.5 to the power 1, and that's basically 0.5. So 0.5 times 10, that's half of, sorry, 0.5 times 100, that's half of 100, and that will return 50 as we got over here. Right. Now we move on to the third one, and I'll just paste when it's 2. And 0.5 to the power 2 is 1 over 4. So we have 1 over 4 of 100. Quarter of 100 is 25, as we have it over here. And when we move on, we have 12. We have 12.5, but the 5 doesn't get returned. an integer gets returned, right? So that's the intuition over there as well. Explicit type casting operator convert a value of a given type to another, right? Float a is equal to 8.9. Now I want to convert it to an integer. Let me use the auto keyword here. Auto b is equal to int of a. Now a is a float, right? We declared the variable a as a float. Now we want to change that float data type status to an integer. So this is the format. You create a variable to store the endpoint conversion of a, and then you write out the data type that you want it to be converted to, and you put this in parentheses. So let's go ahead and print out b to see the outcome, right? We should be getting 8, right? So we have 8 over here returned as an integer. So this number was converted to an integer. So basically that's it. The only thing that I would want to you guys take note is that you can put the parentheses here as well, and it's going to return the same thing. So we run this again when we should be getting 8 as well, right? So the 8 is over there. So we have an integer 8 and we are converting it to a float, right? So we go ahead and run this. We should be getting 8 basically. Yeah, no difference. Even though the data type has changed, of course, but appearance is that there's no difference, right? So we go ahead and comment out all of this. Other operators like the pointers, which will be treated later on object-oriented programming, right? Now, the last thing I want to look at is the precedence of operators. How are the statements being evaluated? Just like in math, you have PEMDAS and you have BODMAS. That's what I'm talking about, right? These concepts are followed as well in C++, general in programming languages, right? So you first evaluate the brackets, whatever in brackets, and you have the off, which is the multiplication, right? And you have division, multiplication again with addition and subtraction. And this is again parenthesis exponential, multiplication, division, addition, subtraction. So that's the order of equations. So to illustrate this, we'll just use this example over here. We have x is equal to 5 plus 7. So let's say this is going to return, let's just say auto, because I don't know whether it's going to be a decimal or a whole number. So let's just say auto, right? So let's name this x1, and then we copy this again and we paste it over here, and this is going to be x2, and for this one we are going to parenthesis over here. And now if you want to explicitly perform one operation over another, this operator, the modulo operator, precedes the addition. So you perform this modulo operator, which is 7 dividing 7 more 2, which is going to be, I think, 1, right? So it will then be 5 plus 1. So this should return 6. This should return 6. But for here, the modulo operator precedes this one, but we don't want that to happen. So we put this in parentheses to ensure that we add before we perform the modulo operation. So what we do over here is 5 plus 7, which is going to be 12, right? Yeah, 12. 12 more 2, which is going to be 0, because 12 dividing 2 would not leave any remainder. So let's run this to print out x1 and x2. Let me just put a semicolon. Run this. So we have 6 over here as the first one, and we have 0 as the second result, right? So you can make whatever you want to precede in the operations come first by putting them in parentheses, so that you ensure that that happens first. Other than that, you would have it run in a format in a like manner with PEMDAS and BODMAS, right? And I hope you're familiar with those concepts in mathematics. So that's it for this video. I hope it really clarified certain concepts, most especially the bitwise operators, which are mostly kind of confusing, and you need some intuitive grasp on them. So that's it for this video. Hope to see you in the next one. Stay safe.